Hello, Lakers. This is David McMayer. I'm coming to you to talk about sample space and probability. This is section 8.3. So why don't you open up your notebooks and you can make an entry in your table of contents for section 8.3. And then we're going to get started. You can open up to a blank page. Section 8.3 details some things, trying to show you how to use organized lists or tree diagrams or area models. We're going to mention Venn diagrams, but that's going to come in a future lesson as well. I think the first thing that we need to write down, and now let me move myself here so we can see the icon there, the idea of sample space. And it's really simple, actually. It's just the set of all possible outcomes for an event. So that yellow and pink statement, that's definitely something that you want to have in your notes as a definition, but then just as an idea in your head, it's really just making a list. An organized list of some kind, or an organized chart, or in some cases you can make a tree diagram in order to do this. There's those different ways, and each of them has their pros and cons. So we're going to try and show you a few different ways here. So in my first example, I'm just going to make a list of all of the possible outcomes of flipping a coin once. And I'm going to consider the two sides of the coin as heads or a tails. So if I made an organized list of that, I would write down exactly what I just said. Heads or tails. There, I'm done. And if I want to box that in, something like this, and then I'm going to try and split that approximately in half, because I know that in terms of probability, flipping a coin once and getting a heads or flipping a coin once and getting a tails are equally likely. We've got a little bit of an organized list there of flipping a coin once and what could happen. We could also make a list of all the possible outcomes of flipping a coin twice. And sometimes people think that you could get two heads, or you could get one head and one tail. Or you could get two tails. And then they look at this as three outcomes, and they make the mistake of thinking, oh, it's a 1 in 3 chance of getting two heads, it's a 1 in 3 chance of getting two tails, or a 1 in 3 chance of getting a head and a tail. And that turns out to be not quite correct. So making an organized list like that might kind of hide actually what's happening here. I'm going to try and use a tree diagram. And a tree diagram is a way of organizing a list in sort of a visual way. So if we've got one coin flipped, kind of marked off here by this point, the two possible outcomes of that coin flip are a head or a tail. And then on our second flip, we would duplicate that and we get a head or a tail. And then likewise, if we got a tail on the first flip, we would flip again and get a head or a tail. Now, if I'm going to list off the outcomes, I have to consider first flip and second flip each time. So this first possibility is heads first and then heads second. The second possibility would be heads first and tails second. The third possibility would be tails first and heads second, and then tails first and tails second. There's actually 4 different outcomes here. And then 2 of those outcomes include one head and one tail. So if you were going to do the probability of getting one head and one tail, that would actually be 2 out of 4, or 1/2, in terms of a theoretical probability, which we're going to figure out in the future here, that what all that means is that if you were to take a coin and flip it twice, and then repeat that experiment lots and lots of times, and count how many times did I get one head and one tail in those 2 flips, in the long run, the overall experimental probability would get close to or match a 2 in 4 probability. Another way that you can do this is by creating an area model. I kind of like these area models. Sometimes people call this like a 2-dimensional grid model. But you can make a list of possible outcomes of flipping a coin 3 times. So we'll just show you another possibility here. So this is another example. So with an area model, all I'm going to do is create an area. And then I want to use that area to list out all of the different possible outcomes. So the first thing I'm going to do is split that area up into 2 equal pieces, because I know that there's 2 different possible outcomes for the first flip: heads or tails. So this entire area on the left is heads on the first flip. And I could take that area on the first, with getting the heads on the first flip, take that area and split that into 2 equal pieces. Each of those areas is going to have heads on the first flip. And then on the second flip, maybe we get heads or maybe we get tails. We could do the same thing on the right side of our diagram. Each of these areas on the right is tails on the first flip, but maybe we got heads on the second flip, or maybe we got tails on the second flip. So what I've just listed out here is identical to what we just had in the tree diagram. Furthermore, we could take those areas and actually split them up into more same-size pieces. So I'm just going to put in another divider here and just show you that both these areas in the top left-hand corner are heads first and then heads second. And then we could get heads third, or we could get tails third. We could split this area in the bottom left-hand corner up into 2 equal pieces. Both of those areas start with a heads first and then a tails second. And then on the third flip, we might get heads, we might get tails. So then I think you can see what we're going to do in the other 2 areas. Split both of those into 2 equal pieces, and then make a list of what could happen. So tails first, then heads second, and then maybe a heads third, or maybe a tails third. Tails first and tails second in both of the areas in the bottom right-hand space. And then possibly a heads on the third flip or a tails on the third flip. Now we could extend this and start asking questions about what's the probability that you get 3 heads, just as an example. And then if I'm going to look at that, I've got to think about there's 8 different equally likely outcomes here, and there's only one outcome that's all 3 heads. It's a 1 out of 8 probability. Probability of 2 heads and 1 tail. Well, I'd have to think about coloring in all of the areas that are 2 heads and 1 tail. So that'd be this area here, this one. This has 2 heads and 1 tail. I think that's it. So just those 3 areas. to a 3 in 8 probability. If I'm going to be consistent, I want to try and keep those colors the same. So that's just a couple of examples. Now in the assigned practice that you're going to be looking at, you will need to consider some different sorts of examples. A lot of times we're talking about tossing a coin or spinning a spinner or drawing something from a bag or a box or a hat. I think in this example we draw some tickets from a hat in one case. So I just want to try and help you understand here that what you need to do is use some sort of a diagram or an organized list to make a list of all possible outcomes. So, for example, in part C here, we're selecting from one of these two bags and then drawing a ball from one of those two bags. So when we're listing out the different possible outcomes there, maybe you start that with the tree diagram. And you list off, I could get bag A, write bag A to be super clear here. Or maybe we could select bag B. And then from there, if we picked bag A, and then I'll just get you started here, but with bag A, there's 5 different balls here. So in a tree diagram, if you want, you can have 5 different branches and list off all of those branches. Looks like 2 of them are green and 3 of them are red. Another way that you can do this is to also list off the associated probabilities. So make that extra notation in your tree diagram. And then here we've got either red or green balls in bag A. And then you could list the probabilities there. So there's a 3 in 5 chance of getting a red ball, and there is a 2 in 5 chance of getting a green ball. So then if we extended this question and asked something about what's the probability of drawing bag A and then drawing a red ball, we would have to multiply the probabilities along those branches. So that overall probability would be 1/2 multiplied by 3/5 or 3/15, 3/10, sorry. In other words, there's a 30% chance of getting a green ball in this red ball in this experiment. Okay, let's move on to another example because I wanted to show you how to maybe use an organized list here to make a list of all of the different possibilities for blocks A, B, C, and D. So this is another example that maybe you could add into your notes. Now what I know here is that if I start to make a tree diagram, and then I'm going to suggest that maybe you don't actually do this. I think the tree diagram gets a little messy. Now if I select box or block A to be first, my only choices for the second block are B, C, and D. And if I select block B first, my only choices are A, C, and D. And then I hope you can see that this tree diagram is going to get messy in a hurry. So sometimes I see tree diagrams kind of spiraling off the page on student work here. And what I would hope that people would realize is that oftentimes it's a little easier to just make an area model out of that. So I'm going to organize my list of things with an area model. You can also just make an organized list of how you're going to do this. So I'm going to cut this area model into some chunks. I've got 4 same size chunks, and I'm going to label them A, B, C, and D. And then within the space for block A, I know that the second block that I draw could be B or C or D. So I can make that list, A, B, A, C, or A, D. And then likewise, I could do the same thing in the other spaces. So we can get B first, then A, B first, then C, B first, then D. Or C first, then A, C first, then B, C first, then D. And I think you can kind of start to see what I'm doing here and how I'm trying to organize my list. So far I've got 2 of the blocks in order, and now I can just need to fill in the third one. So if I just concentrate on this first space where A was first and then B was second, my options for the third block are either C or D. And then in both of those cases, the option for the fourth block is just 1 space. So I'm going to actually wind up cutting this into 2 same size pieces. So I'll have A, B first, and then my combination of the other blocks is either CD or it is DC. And I can make some of those same cuts all the way through. So A first, then C. The blocks left over are B and D. A is first and D is second. And the leftover blocks are B and C. And then why don't you go through and fill out the rest of this, and I will do the same. And what I'm hoping I'm doing here is demonstrating a way of organizing a list so you make sure that you don't miss anything. Oh, that's California, CA. Then left over would be BD. So I've seen this sort of an approach also in, sometimes we do problems where there's people seated in a row and we're trying to list out all the different possible ways that those people can be seated. So this might be friends with first names starting with A, B, C, and D. A lot of times the textbooks like to do stuff like that. Oh, DC. Are you a DC Comics person or a Marvel Comics person? Question for the ages, I guess. So here we've listed off all the different possibilities, and I count 24 of them. Which sort of makes sense, because there's 4 ways to pick the first block, and then there's 3 ways to pick the second block, and then 2 ways to pick the third block, and then only 1 way to pick the last block. So 4 times 3 times 2 times 1 is 24. Another way of doing this in mathematics is to write 4 exclamation mark. It's factorial notation, and that means 24. It's a way of counting. Okay, so for the second problem in our assigned practice, you need to do just that. You need to make an organized list, kind of like what I just did, except this time you have 3 letters, A, E, and T. And then you're going to, first of all, list off all the possible outcomes. And then the second thing you're doing is finding probabilities. So it says find P parentheses spelling eat. Well, I want to remind you that in all of those cases, we're talking about notation. So you can set your pen or pencil down for a second here, and I just want to remind you that what we are doing in those assigned practice problems is using notation and expecting that you understand what that notation means. So when you put a P outside some parentheses and there's a description there, that detailed description of the specific event is the thing that you're trying to find in your organized list. So it just means what is the, or in this case, the probability of whatever that detailed description was. So when you're looking at problem number 2, what is the probability of looking in your list and finding the letter combination EAT? So how many times does that happen in your list, divided by how many things are actually in the total list? Some other combinations here. So P and then rolling a die once and getting a 1, 2, 3, 4, 5. Or what is the probability of rolling a die and not getting a 6? And I wanted to show you something notationally here. So I've listed off 6 different possible outcomes here of rolling a die. You can get a 1, 2, 3, 4, 5, or 6. And I've colored in the possibilities of getting a 1, 2, 3, 4, or 5. So it looks like a 5 out of 6 probability if I consider each of those numbers to be equally likely. Now the probability of rolling a die and not getting a 6, well, that would be kind of crossing off the one space, and there's 5 left over, so it's the same probability. So I wanted to share with you that sometimes we shorten these up, and we might write probability of 1, 2, 3, 4, or 5. And then there's 6 possibilities, and 5 of them would be considered a success, or 5 of them are that desired outcome. Another way of writing this would be probability of not 6. And then sometimes what we do is we say, what's the probability of 6? And then we put an apostrophe there. So this means not. It's just mathematical shorthand notation. But in this case, we would cross off the 6 and then count the rest of them, and we'd have a probability of 5 out of 6. So the reason I did that is because in problem number 3, they specifically mention that notation. So in part A, explain the meaning of the event R apostrophe. In other words, not R. Okay, so you have to try and describe that and be clear in your explanation. The fourth problem that you'll be looking at today involves a pentagonal spinner and a coin. So I have an image there of the front and back of Bitcoin, apparently, and then a pentagonal spinner. So pentagonal is pentagon is 5 different spaces. So I'm assuming those 5 different spaces are equally likely. And you're going to have to try and make either a grid or a tree diagram or a area model, something where you can describe all of the different possible outcomes. For example, you could flip the coin and get a B on the front, or a heads. I don't know what you call the sides of a Bitcoin. And then spin the spinner and get a 2. So that could be B2. What would you call the backside of that Bitcoin? You just call it like computer chip? C? I don't know. You decide. But you are going to eventually here, after you describe the sample space, make a list of all the possibilities, you're going to determine some various probabilities. This isn't incredibly challenging mathematically, so you really practice the notation. Be very clear. So when you're describing your answer, don't just write the number answer for part B, number 1. Write a description there. So like P, and then flipping ahead and getting a 4. Okay, well, I wish you luck on your assigned practice. What am I kidding you? You don't need luck. This is going to be all skill for you. Hope you have a great day.